Hello, my dear students. Hope all of you are doing well. So, good morning and welcome to today's class, that is Physics 1. This course is generally made for undergraduate level BTech degree students. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Badaipur. You can personally meet me at college premises, ground floor physics lab, or you can also send me a mail regarding your query or doubt on this topic or any video class lessons that I have uploaded to my given mail ID. So the mail ID is godphysics6@gmail.com and gopal.chakraborty_gkcem@jisgroup.org. So you can send in any mail ID. Okay. So I have also a YouTube channel. So already lots of video has already uploaded as per your markout syllabus. So you can go through all these video lessons on the subject Physics 1. And if you feel any doubt, feel free to contact me at given mail address or personally at my college. So for this today's course, I am your subject teacher. Now for this today's course, the course pages are www.markoutexam.net and www.markoutwb.ac.in. The physics syllabus is already uploaded in the university website, so students can download the syllabus from the university web page that I have placed you here. The subject titles is Physics 1. The subject code is BSPH 101. It is under the category of Basic Science course. It has a credit 4 and 3 lectures per week and 1 tutorial per week. This course is generally made for undergraduate level BTech degree students of first year. So the computer science, civil, mechanical, these departmental students will going to study this course for their odd semester, and alternatively electronics and electrical departmental students will going to study this course in their even semester, and that in that case the subject code will be BSPH 201. The syllabus is almost same for both the odd semester and even semester. So today now I will going to discuss the rest part of the quantum mechanics, because as you know I have already completed 2 classes of quantum mechanics, so this is the 3rd class. So the topic that I will going to cover in today's class are operators. Operators only for quantum mechanics, that means quantum mechanical operator, characteristics of operator, and different types of operator and its applications. So these all topics are under module 4, that is quantum mechanics. Prerequisite for these topics are elementary idea of quantum mechanics and fundamental idea of mathematical calculations. The course objectives are idea about quantum mechanical operator and its characteristics, know about different types of operator and its applications. After completion of this course, students will be able to calculate the value of each quantum mechanical operator for different cases. So these are the corresponding course outcome. Now, as we have discussed in my last class that wave function play an important role in quantum mechanics. So on the basis of wave nature of the particle, of a moving particle, we can develop wave equation for the particle. There are several ways to develop the wave equation by applying quantum concepts. Okay, so these various classical equation of mechanics, that concept cannot apply here. So you have to apply the concept of quantum mechanics. So actually, in that case, we have to consider all the basic postulate of quantum mechanics. So I have already discussed about that. It is that space-time of the behavior of a particle in physical system that can be described by an associated wave function psi, and the function must be single valued, continuous, and its space derivative are also continuous, single valued, and finite. So from there, I have already discussed that dynamical variables or observables are the physical measurable properties of the particle. So in quantum mechanics, each observable is associated with a quantum mechanical operator. So now today I am going to discuss what is that operator and how we will define or find out the expression of each operator. So before starting with the quantum mechanical operator, first you try to learn what is operator. Okay. So in that term operator, it means which can operate. Okay. So you can compare it with your generator, regulator, etc. Say if I told you what is regulator, okay, in general you can explain that regulator it is a function, that means which can regulate over some quantity, and it will change that value. Okay, that is a regulator. What is generator? So generator is another function, that means which can generate something. This is a general idea. So operator means which can operate over some quantity. So that means when you operate some operator over some particular quantity, it will change that value. Okay. So operator is basically a function. So when you apply that function, that means when you operate that function over some scalar quantity, it will change the value of that scalar to another scalar one. If you operate the operator or that function over some vector quantity, so now it will change both the magnitude and direction of that vector. So you will get a new vector. Okay. So this is the basic idea of operator. In case of quantum mechanics, the quantum mechanical operator, that are also a function. So here, as I have already told you, that position, momentum, linear momentum, kinetic energy, these all are expressed by some operator, that means it's represented by some function. So when you operating that operator or position or momentum or energy over some quantity, it will certainly change that value and will give you a new value. Okay, that means when you operate this operator over some wave function psi, so you will get a new value. Now I will discuss you, or I will show you how you can define or derive each operator step by step. An operator in quantum mechanics is a symbol of certain mathematical tools which transform one function into another. Associated with each measurable parameters in a physical system is a quantum mechanical operator. Such operators arise because in quantum mechanics you are describing nature with waves, the wave function, rather than with discrete particles whose motions and dynamics can be described with the deterministic equation of Newtonian mechanics. So part of the development of quantum mechanics is the establishment of the operators associated with the parameters needed to describe the system. So here I have shown you the some of the operators that's listed here. That is f is a function of x, any function of position, so it's a position operator will be same as f function of x. Second one, that is a linear momentum operator along the direction of x. You can also write this operator along the direction of y or along the direction of z. So the linear momentum operator will be h squared by I del x. Next one, the Hamiltonian operator, so that can be represented by p square by twice m plus v function of x. So like this way you can also define your energy operator, kinetic energy operator, and so on. So I will show you an example that if alpha cap be an operator and fx is a function, then alpha cap operating on fx generates a new function gx. So alpha cap is operating on fx will give you gx. That means after the operation that function changes and gives you a new value. Say now if you put fx value is x to the power n and your alpha cap operator is ddx, then when you operate the alpha cap over fx, that will give you ddx of x to the power n, that means n x to the power n minus 1. So your previous function was fx, so that is only x to the power n, and now after using that operator alpha cap, you will get a new value, and your new value is n x to the power n minus 1. So each dynamical variables is presented by some operator. So operators means it's basically a function. Now each and every operator has some characteristics. So here the quantum mechanical operator has also some characteristics. So these characteristics are: quantum mechanical operators are linear operators. A linear operator has some following properties. That's if alpha cap is a linear operator and f of x is a function, then alpha cfx, that will be equals to c into alpha cap fx. So where c is the constant, so alpha cap over c, that will give you c into alpha cap, or alpha cap c minus c alpha cap equals to 0. Therefore alpha cap always commutes with c. Second one, linear operators obey distributive law. If fx and gx be two function of x and alpha cap, a linear operator, then alpha cap over within bracket fx plus gx, that will be equals to alpha fx plus alpha gx. So linear operators also obey associative law. The Hamiltonian operator capital H cap operating on a wave function gives by corresponding observable quantity, that means eigenvalue, which is the total energy of the system. So capital H cap, this is the Hamiltonian operator. When this operator is operating over some wave function psi, that will give you the E, that is eigenvalue of total energy of psi of x, and psi of x is a wave function corresponding to that system. Now commutator. A commutator in quantum mechanics tells us if we can measure two observables at same time, if the commutator of two observable is 0, then they can be measured at the same time. Otherwise, there exists an uncertainty relation between these two. In normal everyday mathematics, this would be 0. However, in quantum mechanics, the object A and B corresponding to observables, so the commutator tells us that observing the system in different order affects the outcome. Going back to the Heisenberg example, taking a measurement of the position of a particle will disturb its momentum. So this is the commutator. Now here I will show you how can you express an operator commutator. So as you can consider capital A cap and capital B cap, these are two operators, that means two different functions. So the commutator can be represented as within third bracket A cap comma B cap, that's equals to within third bracket A cap B cap minus B cap A cap. So if the commutator value A cap B comma B cap, that is equals to 0, therefore that means A cap B cap will be equals to B cap A cap. So now you can say these two operators are commutative in nature, and if the commutator value, that means within third bracket A cap comma B cap, that's not equals to 0, therefore A cap B cap value is not equals to B cap A cap value. So then you can say the two operators are non-commutative in nature. Next I will show you some problems so that the idea will be very clear to you. So here is an example. You have to show that the two operators del del x and del 2 del x2 are commutative in nature. So you have to prove this. Okay, so how can you prove this? The general idea for an operator to be commutative or operator to be a non-commutative one, how you will prove this? You just take a function, okay, general function fx or phi x or psi x, whatever you want. You just operate the commutator over this wave function or that function. So after operating, you just find out what is your value, and by that value you can easily say whether the operator is commutative or not as per your result, whether it is 0 or it's not equals to 0. So here I have considered a function fx. So I have operated this commutator del del x comma del 2 del x2, this function over fx. So as per the formula of commutator, that is del del x del 2 del x2 minus del 2 del x2 del x, this will operate over fx. So first of all, from the first term del 2 del x2 will operate over fx, okay, and from the second term del x will firstly operate over fx. So in the second step you will get del x will operate over del 2 f by del x2 minus del 2 del x2 will operate over del f by del x. So ultimately what you will get del 3 del x3 over fx, that will be minus del 3 by del x3 fx. So that's equals to 0. Both will cancel out. So as the result of this commutator is 0, so you can say the two operators are commutative in nature. So as your first problem that asked you to prove that operator whether it's commutative or not, the question may also come in this way, that you are also asked to find out what is the value of this operator. Okay, so here this is the second question where you are asked to find out the value of del x comma del t, these two operator, okay, by this formula of commutator or property. So for this I have again considered a function fx, and we operate this commutator over fx, del x comma del t. So as per formula you will get del x del t over fx minus of del t del x over fx. So what you will get? You will get del x del f del t minus of del t del f del x. So ultimately what you will get? Del 2f del x del t minus del 2f del x del t. So both these cancel out, will give you 0. So you can easily say the value of these two operator del x comma del t, that is equals to 0. So both these operators are also commutative in nature. Now momentum operator. Okay, so how can you find out the expression of momentum operator? So suppose the wave function for a free particle in position x direction, that can be represented as psi function of x comma t equals to capital A constant e to the power I within bracket kx minus omega t. So this is the expression of psi. So you just take the derivative of that wave function psi with respect to position x. So if you take the derivative, the first order derivative will give you del psi del x equals to I into k into a e to the power I kx minus omega t. So ik whole multiplied by psi. So this is the value of del psi del x. Now if you multiply both sides by h cut, and if you take the I in the left hand side, so you will get h cut by I del psi by del x equals to h cut k of psi. So h cut by I del psi by del x equals to p of psi, where p is your momentum. So you can see here, you can write the h cut k, that is equals to p. How can you write this thing? As per de Broglie wavelength, you know lambda equals to h by p. So p equals to h by lambda. If you divide and multiply by 2 pi, so you will get h by 2 pi into 2 pi by lambda. So h by 2 pi, that is your h cut, and 2 pi by lambda, that is the propagation constant k. So you will get p equals to h cut k. So this implies the operator p denoted as p cap. Okay, and that value is p x cap equals to h cut by I del x. Similarly, for you can write for y as well as for z. So in three-dimensional case, the linear momentum operator can be written as p cap equals to h cut by I del. Okay, so where del is the vector differential operator, so which includes the three direction along x, along y, and along z. So p, that is linear momentum operator, is it has a value h cut by I del x for one dimension, or you can also write as minus I h cut del x. So this is the expression of linear momentum operator. Now the second case, that is energy operator, total energy. So the procedure is same. Always you have to start with your wave function, known wave function having value psi, its function of x, position and time, that's equals to a e to the power I of kx minus omega t. So this is the expression of psi. So now when you are going to find out the energy operator, so you have to take the derivative of psi with respect to time. So if you take the derivative with respect to time, that value will give you del psi del t equals to I minus I omega of a e to the power I kx minus omega t. So minus I omega into multiplied by psi. So here again the procedure is same. You just multiply both side by h cut and you just take minus I in the left hand side. So what you will get? You will get I h cut del psi del t, that's equals to h cut omega of psi. So it means I h cut del psi del t, that's equals to e into psi. So E equals to h cut omega, you can write as E equals to, as you know, E equals to h nu. So h by 2 pi into 2 pi nu. So h by 2 pi that is h cut, and 2 pi nu, that is your omega, angular frequency. So from there you can write I h cut del psi del t equals to E of psi. That means when you operating I h cut del t over psi, you will get E of psi. So your function I h cut del t is your energy operator. So this is your energy operator, and the corresponding equation is denoted by capital E cap equals to I h cut del t. Next one, potential energy operator. The potential energy operator corresponding to potential energy capital V and represent by V cap. So when V cap is operating over psi, some wave function, the function gets the value multiplied by capital V. So next one, the kinetic energy operator. If the wave function of a system is psi, function of x and t, that is equals to a e to the power I by e, that is px minus et. So del psi by del x will give you a into I by h cut, because your wave function psi is a e to the power I by h cut px minus et. So from there, first order derivative with respect to x will give you a I by h cut p e to the power I by h cut px minus et, that's equals to I by h cut p of psi. Or again the same thing, you just multiply both side by h cut and you just take the I in the left hand side, that will give you del psi by del x equals to I by h cut p of psi. So differentiating psi with respect to x again will give us h cut by I del 2 psi del x2, that's equals to px I by h cut again px psi, or h cut square by I square del 2 psi del x2 equals to px square psi. So from there if we divide both sides by 2m, we will get minus h cut square by twice m del 2 psi del x2 equals to p square by twice m of psi. So as we know, p square by twice m, that is our kinetic energy k. So from there we can write that our kinetic energy operator k cap, that's equals to minus of h cut square by twice m del 2 del x2. So this is your expression of kinetic energy operator. Next one, Hermitian operator. So Hermitian operator are those which represent such dynamical variables whose expectation values are real. So if a cap represents a dynamical variable capital A, then the expectation value of capital A is A within bracket, that's equals to integration u star function of x a cap u function of x over dx. So that is the expectation value of A, where u function of x is normalized. So the complex conjugate of expectation value of A, that can be represented as the previous term whole of star. So that's equals to integration u A star cap u star x dx. Since the expectation values are real, that means the expectation value of A will be equals to the complex conjugate of expectation value of A. So you can write integration of u star a cap u dx, that's equals to integration of u a cap star u star dx. So this equation represents the condition for Hermitian operator. Next one, Hamiltonian operator. So the Hamiltonian actually represents the total energy of a function. So total energy of a particle of mass m moving with velocity v in a potential field capital V can be represented as capital H equals to kinetic energy plus potential energy, so half mv square plus v, or equals to p square by twice m plus v. So H is called the Hamiltonian of the system. So the first part of H, so that means kinetic energy, so that can be represented for the three-dimensional case for x, y and z axis. So it will be sum of px square plus py square plus pz square by twice m plus v. This is the Hamiltonian of the system. Now, as we know, the P, that is a linear momentum operator, the square of this tree, and if you take the sum of this tree, you will get minus I h cut del x whole square plus minus I h cut del y whole square plus minus I h cut del z whole square. So that's equals to minus h cut square within bracket del 2 del x2 plus del 2 del y2 plus del 2 del z2. So that's equals to minus of h cut square grad square. So the Hamiltonian operator can be represented as minus h cut square by twice m grad square plus v. So this is the expression of Hamiltonian operator for three-dimensional case. So now I will explain a numerical or example which is very important for your question. So the question is that prove that x cap comma px cap within bracket, that's equals to I h cat, and also what are the physical significance of these. So as we know from the formula of commutator, so first we consider some wave function f, and now operate this x cap comma px cap over this fx, that gives us x cap px cap minus px cap x cap over fx. So first of all, p is the linear momentum operator, so we substitute that value. So for first case, this linear momentum operator will firstly operate over fx, and for the second case the x value will operate of that fx, then the momentum operator will operate of that fx. So what we'll get, we'll get x h cut by I del x of fx minus h cut by I into x del fx by del x minus of h cut by I f of x. So the first two term will cancel out, and what we'll get, x cap p cap f of x equals to minus of h cut by I f of x. So that's equals to I h cut f of x. That means when we operate this operator x cap px cap over some function f, our value will be I h cut f of x. So comparing these two both sides, we can say that the value of this operator x cap p x cap equals to I h cut. And the physical significance of this equation implies that any position operator and its conjugate momentum operator do not commute. So as its value is not equals to 0, so it is a non-commutative operator. Thus, it is impossible to measure the position and momentum simultaneously along same direction with the same accuracy. This supports Heisenberg position momentum uncertainty principle also. Now, these are the books that you may refer. Okay. The evaluation process is the same. You have to appear for the 70 marks end semester exam and 30 marks as an internal exam. So hope all of you have understand and enjoyed today's class, and it is now very clear to you what is a quantum mechanical operator. So in next class I will start Schrodinger equation. Thank you.